We learned about the binomial distribution. We did some example last time. So we will continue with the binomial distribution. The mean of a binomial distribution is NP, when N is the number of trials and P is the probability of success. The variance is NPQ, when Q is 1 minus P. Remember that P is the probability of success. And the standard deviation is sigma equal to square root of NP. Example. Let X X10 25 be a binomial distribution. Then N equals to 10, P equals to 0.35, and Q equals to 0.65. So the mean of X is P of X equal to NP, which is equals to 10 times 0.35, which is 3.5. The variance of X is NPQ, which is 10 times 0.35 times 0.65, which is 3.5 times 0.65. You can use a calculator to find this. That is 3.5 times 0.65. 3.5 is NP, Q is 0.65. Which is what? 10 times 0.35 times 0.65. Pardon? And the standard deviation is square root of 2.275. What is the standard deviation? One point five? 1.51. Is that correct? The standard deviation. Okay. So here I ask, what proportion of values are within one standard deviation from the mean? What proportion values are within one standard deviation? from the mean. Here the mean is 3.5. Let's say that the standard deviation is 1.5 to make it easy. Then 1 standard deviation from the mean is mu minus sigma mu plus sigma. The question is, what is this probability? This is the proportion of values that are within 1 standard deviation from the mean, which is the probability that x is between 3.5 minus 1.5, 2, and 3.5 plus 1.5, 5. So the proportion of values within 1 standard deviation is probability of 2 less than x less than 3 is probability of 2 plus probability of 3 plus probability, yeah, it's just probability of 2 and 3. So you can use a calculator to find this. What is the probability that x equals to 2? This is the proportion of values within 1 standard deviation. Can you use your calculator to find this? You have TI 83, 84? 84? Okay. You go to second function, then variance, which is distribution. You will see distribution. And then you will choose binomial PDF. Probability of success here is 0.35. Number of trials is 10. We put 2 first. So we have 0.175 or 1.176. What do you get? A distribution is behind the VARS. So you go down, you have to really go down to see binomial. You will pass chi-square, you will see normal distribution, and F distribution, and all those distribution. Then after you see BIN, binomial PDF. So if it, what do you have? Do you have a parenthesis? It's not what we have on the board. We got 0.1756. So that's the probability of 2, 0.176. What about 3? Zero 0.252. So what is this equal to? What do you get? 0.4? Will this be exactly 0.4? Okay, 0.4. I'm just 0.428. Thank you. So about 42%, let's say 43% of values are within 2 standard deviation from the mean on this particular binomial distribution. So what about 3 standard deviation, 2 standard deviation? What proportion is within 2 standard deviation? So we are going to do probability of mu minus sigma. It is probability of 3.5. 2 sigma is 3. Sigma is 1.5. 2 sigma is 3. This is 0.5. Less than x less than 3 plus 3.5, 6.5. So this is the same as probability that 0 is less than x less than or equals to 6. It is f of 6 minus f of 5. F of 0 is the same as probability of 0. And probability of 0 is q raised to power n. But we can still use our calculator. Pardon? If x is greater than or equals to 0.5, then either I say x is greater than or equals to 1, or x is strictly greater than 0. We had a formula when we say P of A less than x less than or equals to B. When we were completing discrete distribution, we said that the probability that A is less than x less than or equals to f of B, where f of x f of B is the probability that x is less than or equal. So I could as well write here that this is equal to probability that x is less than or equal to 6 minus probability that x is less than. So if we put 0 here, we have 0.0134 or 135, 0.0135. Probability of x equal to 0, you can just do 0.65 raised to power 10. Do you have that? 0.65 raised to power 10. What do you get? Yeah. For 0, PDF and CDF will be the same, but that's just for 0. Here we want P of 0. The probability that X equals to 0, that's all failure. Okay. Now let's do for 6. Is that right? Oh, that's not right. We are looking for X is less than or equal to 6. We should use cumulative. For 6, cumulative. I say use PDF of CDF for 0. But for 6 is less than or equal to 6.974. Do we understand this, Mason? I'm working with Maggie because she's the one using our calculator, but I want to know that you guys are understanding what we are doing. I am using this scientific calculator on the board. Jacob, are you okay with that? Are you following us? Okay. So this is 0.974. 0.974. This is X less than or equals to 6. This is about 0.9. 0.9, I'm sorry. It's 0.96. So this makes about 96% of values are within 2 standard deviations from the mean. About 96% of value. If you remember what we call the Chebyshev theorem, will this be consistent with the Chebyshev theorem? Do you understand what I'm saying? The Chebyshev theorem tells us that at least 1 minus 1 over k squared values are within 2 standard deviations from the mean. And k here is 2, that is 75% of value, at least 75% of values are within 2 standard deviations from the mean. So we have computed here and we get 96% of values are within 2 standard deviations from the mean. Is it consistent with the Chebyshev theorem? Yes, it is. Now let's compute the coefficient of variation. The coefficient of variation is the standard deviation divided by mean times 100%. Here the standard deviation is square root of NPQ and the mean is NP. So this is kind of square root of NP times square root of Q divided by NP, which is square root of Q over NP. The coefficient of variation is Q over NP, which is square root of 65 divided by 3.5. That's 100%. The next distribution is one which is close to the binomial distribution. It is called the geometric distribution. No, I can explain this proof. I plan on explaining this proof. So I will explain the proof by using. So to prove this, consider a binomial random variable x equals to 0, 1, 2 up to n. Let xi be the number of success at the ith trial. So the idea behind this is x0 will be 0, 1. And the first trial, you may have 0 or 1. First trial, you might have 0. At the second trial, you might have 0 or 1. The number of success. So, for example, you toss a coin 3 times. What is the number of heads? If you have no head, if x equal to 0, it could be that x1 equal to 0, x equal to 0, x equal to 0. So what I'm trying to say here, I want to write it here so that if you want to check it out, you can see. X equal to 0, 1, 2, be a binomial random variable. So it means there are n trials. N trials. Let x1 be the number of success on the first trial. The number of success on the first trial is x1 on first trial. X2 on second trial. And we continue this way. Xn, the number of success on the n trial. So then x equal to sum of the xi. Simply put, think about if there are 3 successes, then there was 1 success in one of the trials, another success in another trials, another success in another trials, and all other trials has xi equal to 0. Does that make sense to you? Xi is the number of success on the ith trial. So if the first trial there is failure, then x1 equals to 0. If the second trial there is success, x2 equals to 1. Third trial failure, x3 equals to 0. Fourth trial failure, x4 equals to 0. Can you understand what I'm saying here? If I define xi as the number of trial on the ith, the number of success on the ith trial, then the number of success at the end is the number of success on the first trial plus number of success on the second trial plus number of success on the third trial, and so on until the end trial. That's just what it means. So the xi are independent because there are independent binomial trials. So this random variable xi are independent. So because they are independent, we can say that E of x equals to, this does not require independence actually, which is equal to n mu. I'm sorry, np. Which is equal to np. This is because E of xi is a Bernoulli random variable. We learned that the Bernoulli random variable has mean p and variance pq. So we will have E of xi equals to p, and there will be n of them. That's why we get the np. Because of independence, the variance of x will be the variance of sum of the xi equals to 1 to n, which is because of independence, variance of the sum is sum of the variance. And all of them have the same variance PQ from the Bernoulli distribution, which is NP. So here is the proof of the mean, variance, and standard deviation of the binomial distribution. You have this proof here, but it is not the proof is here. So the same proof is here. So this is just the application of the properties of expectation and variance. A geometric distribution is like a binomial in the sense that we have a sequence of independent Bernoulli trials. But here, it is not a finite sequence because we will keep performing the binomial, the Bernoulli trials until we get a success. And X will be the number of failure before the first success. It's just we did one of these examples in the past. So I want you to know that some people define the geometric distribution as the number of trials, but in our course, in Math 215 and Stat 205, it is defined as the number of trials on the first success. In this class, we are defining it as the number of failure before the first success. So the main difference is that we start from 0 and they start from 1. If you are counting the number of trials, you cannot have success with no trial. So we have that X is the number of failure before the first success. So if you get success at the first trial, X equals to 0. If you get success at the second trial, that means you failed the first trial. So the probability distribution, I will move from here to explain. X to 1, 2, and we can go to infinity. This is the number of, X is number of failure. Before the first success. For example, if X equals to 0, the outcome is success. If X equals to 1, outcome is failure, success. X equals to 2, outcome is failure, failure, success. In general, the probability distribution is probability that X equals to K equals to 1 success, the last one, times Q raised to power K, the number of failure. So the geometric distribution is defined as P of X equals to K is equal to K, P times QK. Next question we want to ask is, what is the probability generating function of a geometric distribution? What is the probability generating function of a geometric distribution? We could do the same for a binomial distribution, but it wasn't very useful in the proof. But this is going to make our proof easy as we define the probability generating function. So the probability generating function of a geometric distribution xp is h of s equals to e of sx. This is the definition we had of a probability generating function, which is equal to the sum of sx times p of x, which is equal to the sum of xx times p u raised to power x. Which is equal to t sum of sq raised to power s raised to power x. Remember the probability generative function, we learn it at the end of chapter 4. I'm sorry, chapter 3. This was the probability generating function of any random variable x. We want to use it now in chapter 3. So we want to do this sum. You remember what this sum should be? We are going to get used to it. Remember that sum from 1 to infinity of r, okay, will be r plus r squared plus rn. This is limit as n tends to infinity. So which we define as limit of n, I'm sorry, not n, of r minus rn plus 1 divided by 1. Which happen to be r over 1 minus r, provided absolute value of r is less than 1. Provided absolute value of r is less than 1. Oh, here we are starting from 0. Sorry. X is from 0 to infinity, not 1. I'm sorry for this. But the difference is not much, you know? We are going to put 0 here. And when we put 0 there, what will make the difference is that we change this one. What do we change this to? Can anybody tell? If we are starting from 0, what do we change this to? To 1. So we will define h of s to be equals to p over, the p is this p, and this sum from 0 is 1 minus s. The domain of this function, if you are doing calculus and you are asked to find the domain of this function, the domain of this function is provided absolute value of sq is less than 1. That is, absolute value of s is less than 1 over q. This is the domain of this function. You are used to some domain like square root, fraction, and all that. You can get to some type of problem like this one, where you will want to determine the domain by thinking about the rules that led to the definition of the function. Let's do some calculus here. What is s prime of s? What is s prime of s? Anybody remember? The derivative of a fraction, the variable here is s. Yes. One over u prime minus u prime over u squared. So what is u here? One minus s cubed. And what is the derivative? The variable is s. What is the derivative of 1 minus s cubed? Q is a constant. Minus q. So we will have minus q at the numerator, right? So this is going to be pq over 1 minus sq squared. And what will be h prime of 1? There is one negative here. Okay. And what is h prime of 1 here? S equals to 1. pq over 1 minus q squared. It is pq over p squared. It is q over p. We are going to learn later. Find the second derivative, homework. Find the second derivative of the probability generating function h of s. So the mean of the geometric distribution is q over p. So the mean of a probability generating function is q over p. The variance is q over p squared. That's what we will do next time. And the standard deviation is not this. Square root of variance, square root of p over q. Square root of q over p, I'm sorry. So to complete this, please find the second derivative of this h prime. It will help us to complete. Okay. We continue next Friday with the problems on geometric distribution. And we will look at the negative binomial distribution. Aisha, we are done.
Thank you. See ya.
Thank you. Take care.